You hear and see me, guys? I've been pressing the start streaming button for the past like minute or so. Hopefully, you guys can see me just fine. All right, I see myself, and OBS is saying that the volume is good, so I'm going to go ahead and continue. All right, so last Wednesday, I was pretty sick. I'm feeling a lot better now, and that should make for a better stream. We were talking about galaxy colonization, and basically coming up with a way of calculating how long it would take to be able to colonize our galaxy. Now, along with that, I put down a few assumptions and requirements for the calculation, and they're listed here. I'm not going to actually like verbally say them out loud, but we kind of made it partially through the calculation, and while I was offline, I finished the rest of the calculation on my own. Now, of course, because of the fact that I finished it by myself, I want to be able to include your input. So if we want, we can always modify values and see what sort of new results we can get. All right, so with that said, let's go ahead and continue where we left off at the very least. Let's walk through what we were able to get through to the point where we stopped in our last stream. So, if I'm not mistaken, Hanny asked two good questions at the very beginning, which was, what's the fraction of solar type stars? And there was one more question, what's the average distance between the solar type stars and the Milky Way? We went through the calculation, which is seen here, and basically it relies on doing a little bit of math with the initial mass function, which we've talked about in previous streams. Now, when we did this initially, I defined the mass range for solar type stars to be somewhere between 1 and 2 solar masses. And that was not a really good mass range to use for solar type stars. So in this case, I just assumed that all the solar type stars are G-type stars, and I'm using that, well, roughly the mass range that corresponds to G-type stars, which is roughly somewhere between 0.84 solar masses to 1.15 solar masses. And using that particular mass range, we end up getting that there's a rough percentage of roughly 2% of the stars in the Milky Way that are solar type stars. And then we continue our calculation. And of course, from there, if you know that there's roughly 2% stars are solar type, and you know the total number or have an estimate for the total number of stars in the Milky Way, you can, of course, get a number for the number of solar type stars, which is roughly around 2 billion solar type stars. The next step was answering Henny's second comment about the average distance. Now, to get at this, what you can end up doing is you can take the reciprocal of the number density, which is represented here by the n sub solar stars, the number density of solar stars. And we calculated this by taking the volume of the Milky Way and dividing it by that number that we had just calculated above, which roughly left a volume. Now this should be interpreted as a volume per solar type star of something on the order of 10 to the 51 cubic meters. That's a really, really, really big number in terms of meters, and it's kind of hard even for me to even like imagine what that is. So, continuing from there though, because you have essentially a sphere that encompasses a single star, if you calculate that radius of that sphere, you kind of get a rough distance between each solar type star. So continue the calculation, and basically solving for that radius of the sphere that encompasses a single solar type star, we end up getting something on the order of 12.3 parsecs per solar star. Now, I converted to parsecs for meters because, again, I can't imagine meters, that big. So parsecs makes a little bit more sense. Now, comparing this to the actual like average distance between stars, which is roughly like around 1 parsec per star, we're seeing here for our calculation that it's a factor of 12 more if you consider just simply the solar type stars instead of considering all stars. All right. So that's kind of, and I think we actually went a little bit further than that. But from what I'm remembering, I know that we were able to at the very least get through that much of the calculation. And then we continued though to talk about, well, now that we went ahead and calculated the number of solar type stars and the average distance between them, we can move on and start talking more about, the ability to be able to populate a planet, or for it to at the very least reach the maximum number of occupants that we defined earlier to be 8 billion people, which is kind of roughly the number that we currently have here on Earth. And so the idea was that we'd use an exponential function to be able to do this, defined by the equation that's represented here or seen here in the very center of the screen. Now, I want to make sure that I'm looking at comments and I'm not like just leaving everyone like as far as the explanation is considered. All right, I don't see any comments or questions, so I'm going to go ahead and continue. All right, so the equation that we use is that the maximum population that we can achieve has to be equal to some initial population that we start off with times the exponential function raised to the rate at which the population is growing times the amount of time it would take to reach the maximum population. And of course, we simply want to be able to calculate the amount of time that it will take to reach the maximum population. So we solve for T max pop. And we get the equation that we see here in the center of the screen. And really right now, once we have this equation, we're basically just plugging and chugging in values. And so I actually went online, and I mean, you guys can do it as well, but I basically just went online, and I quite literally just typed in annual population growth rate. This one says roughly around 1.1%, but I think one of the other results that I ran across is roughly around 1.2%. So I used the value of 1.2% to be able to calculate this, to help in calculating the amount of time it would take to reach the maximum population size. And so let's go back. And that's an important portion of the calculation, of course. However, another thing that we have to take into consideration was that I assumed earlier in the assumptions, we're assuming that while traveling from one planet to another, the spaceship is only able to handle at max around 1,000 people. And that while the spaceship's traveling from one planet to another planet, or from one solar system to another solar system, that the number of people on the spaceship stays constant. So essentially, we're seeding the new planet 1,000 people to start off with, which is what P naught or P sub 0 corresponds to. So we plug in all this information into our equation, and we see that the amount of time it takes for the population to reach the maximum is 1,324.58 years, or another way of putting it, 1.3 millennia. Now, this is a much smaller amount of time compared to how long it took, of course, for humans to reach the current population size that we have now today. Now, of course, we don't have to worry about things like evolution and stuff like that. And now that I think about it, I guess while they're traveling, from one planet to another, I mean, that might actually be enough time, to be able to undergo some form of space evolution. But of course, in this calculation, we don't consider any of that stuff. We're assuming that the humans stay human throughout the entire trip. So no cosmic rays or some radiation is going to be able to, manipulate or somehow help change, or the conditions of space will not change the human structure in any sort of way. So we stay human over this 1.3 millennia amount of time for the humans at some other planet to reach maximum population. So yeah, the max population per Earth-like planet is 8 billion people. 4 quadrillion is, oh my god, that's insane. That's an insane number of people on a single planet. But yeah, we can always think about it if we were to lower the number from 8 billion to 1 billion, how would that affect the calculation? At least for the amount of time it would take for the population to reach its maximum. That let's see. Ooh, that natural log really makes things not so fun to deal with. So basically, within the natural log of our equation here, we'd have to change the 8 to a 1. And so that would modify things, I think, somewhat significantly, actually. It would modify things a lot, I think a lot. By a couple of factors, at least. And so, I'm not too sure I understand what you mean. That is a planet that is one whole building. And so we get a time for max population for a single planet of 1.3 millennia. And so moving on to the next part of our calculation, we want to now consider, well, what's the amount of time it would take to travel from one planet to another? And that's actually probably the easiest part of the calculation because we can just go ahead and use our good old equation for velocity, where the time it takes to travel from one planet to another planet, or you could think of it as from one solar system to another solar system, is basically the distance, but the average distance between the solar systems divided by the velocity of our spaceship. Now, this is one of the things that's it's very interesting to talk about whenever you bring up a calculation like this. And a lot of people may ask, and even in our discussion on Wednesday, we were talking about having spaceships that had FTL drives, being able to travel at or pass the speed of light. Now, in this calculation, I present two different travel times, and only really use one for the final calculation. But the first travel time I'm using, let's make sure that you guys can see everything just fine. The first travel time I'm using is I'm assuming that we're going to use an actual speed that we're capable of achieving. And so I went looking online, and I found that the Voyager 1 space probe has a speed somewhere close to 40,000 miles per hour, which is insanely fast. By the relative to the speeds that we're reaching here on Earth, like in cars, for everyday drives. However, in this particular unit, it's not very useful. So I went ahead and made the conversion from miles per hour to parsecs per year. And so we see now, in terms of a parsec, and the way in which you should think about a parsec is that a parsec is the average distance between two stars. Um, and so, in terms of parsecs per year, this corresponds to a very, 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 very insanely small fraction of a parsec over the course of a year. So we're not really going anywhere too quickly. And so by plugging in these values of 12.3 parsecs being the average distance between solar type stars, divided by the speed of our spaceship, which we're assuming to be roughly the speed of Voyager 1, which now currently is like at the edge of our solar system right now as I speak, um, using that parsecs per year value for our spaceship, we end up getting that it will take roughly around 703,000 years, essentially, or 703 millennia. And so, just comparing this value relative to the amount of time it takes for a planet to reach maximum population, given the conditions that we've assumed, this, of course, will be the major factor in our calculation. So basically, just travel time from planet to planet is the major portion of our calculation. Now, of course, like I said, we brought up the fact that the space shuttles can probably even move. If we were to assume they could move at speeds comparable to the speed of light, I decided to go ahead and figure out that travel time as well, assuming that the shuttle's moving at the speed of light. Let's see. So Larry's stating, after 100,000 years or so, would we recognize the? Haha. So yeah, that's a great question, and I was kind of talking about that a little bit earlier. So we have to take into consideration with that evolution, right? Um, with this calculation, and I was going to kind of cover this at the end of our discussion, but we're assuming there's some hidden assumptions here, right? We're assuming that the planets they're going to are very much like Earth, or are exactly identical to Earth. We're assuming, of course, the stars are very similar that of our sun. Um, the planets, of course, we're assuming that they're in the habitable zone of that star. We're assuming a lot of stuff, and of course, I mean, it's not coming up, immediately within our equation that we're building here. But oh wait, Henny states, and what about body modification to adapt to a new planet, both biological and technical? That's a very good point. So yeah, we're basically assuming a ton of things here. I mean, because who's to say that the planet they move to, that the materials there are very much different from what we have here on Earth? The atmosphere, of course, can be very different. A lot of things, which of course all of these conditions affect, you know, our biology, especially over long periods of time, and the technology that we can, produce on that planet, or how well our current technology can handle, the conditions of the planet. So, but yeah, I decided to go ahead and just do the calculation, assuming that the space shuttle is moving at the speed of light. And so the key thing I want to note here is that if you take the speed of light and you put it in miles per hour, which is the unit I'm more familiar with, um, I know outside of the United States, things are in terms of like kilometers per hour. Um, but in terms of miles per hour, we're talking roughly like on an order of 10 to the 8 miles per hour. That to me is, again, insanely fast. And to put it even into more like better perspective, this is 0.3 parsecs per year. We're traveling roughly a third of the distance between, the density of stars, or not the density, but the average distance between stars. That's insane to me. I mean, that's really moving. That's moving really quickly. But with that calculation, right, just making that simple change of the speed of the spaceship, it would take a total time of somewhere around 41 years to go from solar system or star system to star system, assuming, of course, that the whole star of the system is solar type. That significantly would reduce the amount of time it would take to populate the galaxy. In fact, I mean, at this time, on these time scales, I mean, you could probably populate, colonize um, multiple galaxies. I mean, like, that's insane. So, but yeah, with the rest of the calculation though, we're assuming values that are more realistic and are, well, at least realistic compared to what we've currently been able to achieve. So for the rest of the calculation, I use the 703 millennia figure for the travel time traveling between planet to planet. All right, guys. So this is where the math kind of gets a little bit more interesting. Let's put it that way, a little bit more interesting. Hey, her, you. Her, whoa, okay. Well, hey, her. How's it going? And so, right. And so, right, I want to take a quick moment to step away from the calculation and kind of get a sense of what's physically happening as we're colonizing the galaxy. And that's not what I wanted to bring up. Let's do this. I think I do that. There we go. So this is a quick drawing I made to kind of get a simple idea of what's going on here. So, of course, we'll assume that we're starting off at Earth, which, as far as our diagram is concerned, is at the very center of the diagram. Or better yet, the circle can represent our solar system. And at the very center of that, roughly there's the sun and Earth, right? Now, on our first voyage out into the void, right? Traveling from Earth to another star system. Remember that in our previous conversation on Wednesday, we assumed that each planet essentially has. We'll assume that the materials that are available are enough to build two space shuttles that can travel, interstellar space. And so, on that first leg of the journey, represented by N1, we send two shuttles out, and let's just say they go in opposite directions, and they each go to their respective star system. Well, now that we've made it to the new planets, right, with 1,000 people initially, those thousands on the two planets now will build to become 8 billion per planet. And we're also now another hidden assumption. We're assuming now that the amount of time it would take on both planets to go from 1,000 to 8 billion people is roughly the same. But again, it really heavily is dependent upon the conditions of the planet and the system the planet's physically within. So we're assuming the amount of time it takes on each planet is the same. We're assuming the amount of time it takes to reach both planets is the same. Now, 8 billion people has been reached on both planets, sister planets that we've colonized, and now it's time for them to build two more space shuttles and send those space shuttles from each planet, out into the void again to find a new planet. Well, if you notice, this is basically just a binary process. With the first planet, Earth, we made two shuttles, which corresponds to two planets. On the two new planets, they themselves now make two more shuttles per planet. That's 4 shuttles in total, and the process will keep continuing. So the number of shuttles that are being built is going to be equivalent to essentially the number of planets that are being colonized. And so hopefully this diagram makes sense of it all. But the reason why I put this whole N1, N2, and N3 is basically to represent the number of times that we have to keep making these mass, travel movements going from the one planet to a new planet. And so, oh, thank you very, very much. Wow, I said it perfect. Your name, I said it perfectly the first time. Okay. Um, so Hanny, and assuming they aren't trying to inhabit a planet surround. Oh, don't let's not even get into all of that, right? Talking about black holes. I remember on Netflix actually. It's a reboot of the what is it called? Danger, Will Robinson, Danger. I'm forgetting the name of it. But in the reboot of this TV series, thank you, Lost in Space. In the reboot of the TV series, um, the mother of Will Robinson goes up into space to see what's going on, and happens to notice that there's a black hole in the system with them, and it's eating the star at the center of the system, and or like exactly like Interstellar as well, right? And there's a bunch of different things you can get into with that, right? With time dilation and stuff like that. If you're close enough to the black hole, and that could affect the calculation as well if you think about it. But we're not going to get into that. That's making the calculation far more complicated than I want it to be. But yeah, I mean, there's a lot of things you have to consider, right? And so this is assuming that the destination planets contain the resource. Exactly. Very good point, Herleyu. I mean, like you gotta consider that, right? That the materials on the planet have to be, what you're used to. So, all right, this is the diagram that we're working with, and so we're using this diagram basically to build the rest of our, our to help us with our calculation. So going back, so I think I can just simply do this. Boop, there we go. So going back to the calculation, like I said, this is where the math gets interesting. You have to take into consideration this is a binary process, and that basically we're summing the we're summing our basically our the number of stars that we're going to end up essentially, colonizing, or not stars but planets, or number of solar systems that we're going to be colonizing, is basically equal to the sum of 2 to the I power, where I goes from 1 to n and not 0 to n, because 0 would correspond to Earth, of course. Now, I didn't really explain that with the previous diagram, but yeah, n equals 0 is Earth. N equals 1 is all the other travel, the mass travel segments that we had in the diagram. So, of course, that sum, me personally, I couldn't remember how to calculate, how to reduce that sum. I ended up looking it up online, and basically it's 2 to the n plus 1 minus 2 in this case. It would be minus 1 if you include the n equals 0, but we have to get rid of that term. So, breaking that down, we basically get 2 to the n power times 4 minus 2. And solving for n, this is always a neat little trick you can do whenever you're dealing with powers. If you know the base, for example, 2 to the n, if you want to isolate the n, and if the base number is 2, you simply just take the log base 2 of 2 to the n to isolate the n value. The same thing if the base were like 10, for example. If it was 10 to the n, you take log base 10 of 10 to the n to isolate n by itself. And so that's exactly what I did. I isolated the n, and basically we end up getting that n is equal, more precisely, n is equal to 28.89735. But you can't have fractions of these mass movements from one planet to another. It has to be an integer value, so I rounded it up to 29. And so basically using that rounded value for n, so basically we're going to do, if I go back to my diagram there, we're basically going to do 29 of these mass movements, going from solar system to solar system. And we're assuming, of course, that when the space shuttles leave one planet to go to another, they're all leaving at the same time to do their travel. And as populations are growing on planets, they're all growing simultaneously. And again, this is for the ease of the calculation. So, excuse me, we finally can get to a total time it takes to colonize the galaxy. So I basically went ahead and made the proper substitutions. In terms of calculating the total amount of time it takes to populate all planets, you take our value n that we just calculated and multiply it times the amount of time it takes to reach maximum population. And you do a very similar thing, of course, for traveling from planet to planet. You take our value n and multiply it times the amount of time it takes to travel between, just two planets. And basically what you end up getting is that the total amount of time it takes to colonize the galaxy is something on the order of like a couple tens of millions of years. So 20.4 million years for this calculation. Now, when you think about that, 20.4 million years to colonize the galaxy, and this is kind of using, realistic values for the colonization process. That, in the grand scheme of things, is a very short period of time. A very small period of time. I remember in one of our previous calculations, we calculated the lifetime of the sun, and the total lifetime was something about was somewhere on the order of like 10 billion years, and we're roughly 5 billion years through that. So we have roughly 5 billion years more to go before the sun moves off the main sequence and becomes a red giant. But when you think about that, this is a fraction of one of those billion years. So if we were to start this process right now, like right now, if we were to start this process, we would be able to colonize the galaxy before the sun, essentially started its death process, which I thought was pretty interesting, actually. There's a few other time scales you can make comparisons to as well, right? What would be a really interesting calculation is to compare this value to how long it takes the sun, to make one complete orbit around the center of the galaxy. I used to remember the orbital velocity of our solar system around the center of the galaxy, but I can't remember it off the top of my head right now. I'd have to look it up. But yeah, basically you take that and you can figure out, you know, knowing that we're at eight parsecs, 8 kiloparsecs away from the center, you can figure out how much time it takes. So I know I've just been talking and talking and talking. I want to be able to look at everyone's comments here, so I'm going to scroll back a little bit. So imagine n equals 15. Right, that's going to be much. It's going to be much smaller, right? Wait, I'm seeing cannibalism here. All right, this is a very interesting path for the conversation here. Cannibalism. Let's see. Imagine a n equal 15 civilization. So basically, oh, I think I see what you're saying. I think you're saying like at the nth leg of this expansion, the 15th leg of the expansion, they decide to start eating each other. Oh man, that would be horrible. If everything works like clock, exactly, everything would have to work like clockwork, Andy. That's exactly right. After 20 exploratory missions, there would be a million ships launched. Yeah, if I'm not mistaken, yeah, I think you're right because the number of planets is equal to exactly the number of ships. Well, no, that's not right, right? Because each planet has two ships, right? But yeah, that's insane, right? That's another thing to think about. Do we have the resources? I mean, I would assume, of course, a single planet would have enough resources to be able to build two ships. Assuming, of course, the planet is similar to that of Earth's, right? Earth's resources. Just I mean, really, the values I'm using, some of which come from Star Trek, as far as the number of people who are gonna physically occupy a single spaceship. Um, Even like with Star Trek, right? They're building many of those. They're mass producing those space shuttles, and of course, I mean, they're using materials that are within the solar system. But I mean, I would think to build two of them. I mean, I think we have plenty of resources here on Earth to do that. I think. Um, yeah, I loved Interstellar. I loved the it seemed really interesting. It was a very interesting movie to me. And there are times when you're looking at a movie and you're thinking about how realistic is the science, and I mean I liked it. It was nice. That and also the other movie, Gravity. Those are like at the top of my like favorite science movies. So you said that the you're so I'm seeing here it's more about population propagation. Wait, are you're saying that the travel time is negligible? Well, in this case, the travel time is is I think is what's taking the most time, right? It's based off the calculation. Um, you're talking about almost like a factor of 700 in difference, right? Yeah. So I think I may have read something like that, right? About the sun being able to get hot enough to boil the oceans. Because believe it or not, while um while on the main sequence, the sun is kind of in a stable state. Its temperature over time will rise, um, but the amount that it will rise by will be, I think, from my understanding, will be significant enough to be able to boil the oceans. I think I may have read that somewhere at some point. So send out some sort of like 3D printer to be able to produce produce these space shuttles for us. Yeah, that would change the amount of time, wouldn't it? Well, what? Well, would it change the amount of time? Because in this calculation, we're assuming that while the population grows, the space shuttles are also being built as well. And yeah, so Hanny, that's another very interesting point you bring up here about invasion, right? What if there's other life out there, right? That could really be like a monkey wrench in our plans to for galactic conquest. And so initial habitat construction being pre-built long before transit would definitely cut down on risk of expedition death with an established base built before arrival. Indeed, I agree with that. But yeah, that's I mean, there's so many different factors, right, that we have to think about with this calculation. And I mean, honestly, I mean, this very simple, essentially like very basic calculation. This doesn't do the problem, enough justice. I mean, you have to really think, really hard about all these other factors that we're not talking about here, or that that's not that we're not talking about, but that's not being presented in the calculation that we've just done. Um, and who's to say? I mean, if we are able to increase the amount of the speed that our space shuttles can travel, as far as interstellar travel is concerned, if we're able to do a significant change to that, I mean, that would cut down the amount of time it would take to colonize the galaxy significantly, especially if we were able to travel at the speed of light. But I don't see that happening anytime soon. Oh, remind me, what's Kessler's syndrome? So the speed that we're using in our calculation is 40,000 miles per hour, um, which is kind of roughly around the max speed of Voyager 1. But I also presented another speed for our space shuttle, which was the speed of light. And with that speed, and with the other assumptions that we've assumed, we get a total travel time from planet to planet of roughly 41 years. So basically, within a single person's lifetime, you know, they could travel from planet to planet. And then it's more realistic that you can keep then it's more realistic that you can keep the population size at 1,000, right? I think it'd be very difficult to keep the population size at 1,000 over, what was that, 703 millennia or 703,000 years. Keeping the population size at 1,000 is just going to be extremely difficult. Let alone, have the resources to make the trip. So, so Hanny states here that is when a ship breaks apart, causing other ships to break apart from the debris. Well, in this situation, we're assuming that we can assume that the ship's going to be far enough apart from one another that they won't, if something happens to one ship, it'll be completely independent of the other ship. Um, for some good reason, I am not remembering this acronym here. Yeah, so please remind me, what is soul? Oh, speed of light. Okay, all right, I'm with you. Um, so yeah, Assuming that, so if I scroll back up, right here. So assuming that the average distance between solar type stars is 12.3 parsecs, or roughly 12 parsecs. Traveling at the speed of light would allow us to travel from planet to planet in 41 years. So basically, what is that? Right, a light year, right? A light year is equal to zero point 0.3 parsecs. Oh, I'm with you. I am being so stupid right now. Of course. All right, that's exactly what happened in gravity. You even said it earlier. Yeah, when that happened, and it was her first time being up in space. He handled it, handled it so, calmly. Talking about George Clooney in the movie Gravity, he was just like, so calm about it, and she was freaking out. And that's exactly where I would have been. And I don't think I would have ever been able to get out of that state. I'd have been, like, you know what, it's over. Yes, astronauts are amazing. As mysterious and as interesting as space is, I don't think I would ever, ever, ever want to go into outer space unless like I absolutely had to. I mean, it would be like last resort. I mean, all the volcanoes and all the natural disasters on Earth can be like going off simultaneously. If there is a piece of land that is safe, I would rather go to the piece of land that's safe than go into outer space. Well, yeah, right. Eventually, I guess traveling to outer space, after so many times of doing it, would become the norm. Oh, I'm sorry. Ooh. Oh, that's a very good question there. So this is actually 41 years of traveling at relativistic speeds in space from one planet to another. So we're not even on the planet yet, and so Halayu brings up a very good point, right? We're traveling at these relativistic or at the speed of light, um, we're traveling relativistically, and so we'd have to talk about time dilation. And the key thing here is also like, well, people wouldn't really age, one, right? I mean, the amount of time, or the amount of time that it would seem to them that they've actually been on the shuttle would probably be a lot different compared to how we're perceiving it. So that's another very good point there. And I mean, our calculation does not take into consideration, relativistic effects. And that's another good point, Hanny, right? I mean, 41 years of time of being able to travel, from one planet to another, that's nothing, right? That's nothing for the person, at least for the person that's on the space shuttle traveling, at that speed. But then again, yeah, I think with one of the paradox problems for time dilation, if they were to travel to the planet and travel back, when the person would come back, they'd still be much younger than what we perceive them to be. The twin paradox, right? One twin stays on Earth, one twin goes out into space, or goes out somewhere, and they're traveling at the speed of light, or traveling relativistically. And you notice though that upon return, I think the twin that was traveling relativistically is younger than the twin that just stayed at non-relativistic speeds. That does seem like it's a long time, right? But I mean, it does seem like a long time, but it's not really a extremely long time, right? When we start talking about relativistic, effects with our problem here, um, you kind of see though that you can easily see that the amount of time it would take to to colonize the galaxy is not going to be in the order of millions of years. It'll be much 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 less than that. And at that moment, and I think Herleyu said this earlier, you know, if we're doing relativistic travel between planets, then the major factor would now be become populating the planets. That's another good point, Hanny. Right? That's another great point there. That for the people that are traveling much faster, time is much different for them, right? They can do a lot more things. Another way I like to think of it is and again I love to be able to use like movies and stuff to kind of explain things. I remember watching an episode of Flash, and basically someone set off a bomb or a nuclear bomb, and basically the Flash was able to zip around town, and you could kind of see the blast slowly expanding, But the Flash just went everywhere, all around town, talk to people. For him, he was able to do a lot of things, but in a very small amount of time. For everyone else, I mean, they weren't even aware that he was doing the things he was doing. So the same would be the situation for this, right? The people that are moving at a much faster speed, you know, time is much different from them. They can do a lot more things. Yeah, Adam. I agree with you on that. We'd more than likely like kill ourselves because of multiple things. If the fact our population is growing exponentially, and we just run out of resources, and that doesn't kill us, there'll be other things that we end up probably doing to kill us. Elon's group would still be on Mars. Okay, it's actually interesting. Let's see. The travelers have more. Oh, that's a good point, Herleyu. That's right, because if they do a boomerang, they've now moved from an inertial reference frame to an accelerated one, and that would change things. Man, guys, I've loved our conversation here. And honestly, I mean, I wasn't even this went much longer than I expected actually. And I was worried that while I was walking through, explaining the math and stuff like that, I would lose everyone's interest. But like based off of our conversation, it's the exact opposite. So I'm happy about that. Well, guys, the time is now 1:26 p.m. I have some other things I have to get to. Um, Andreas, Dr. Plazos is kind of waiting on me to finish some plots up so we can continue making progress with the paper we're writing right now. So I am going to go ahead and get to that. And I will be back next week on Wednesday and Friday after Daily Space. And so I look forward to seeing you guys then. And again, guys, thanks for a great conversation. All right. Bye.